On the Flurry blog, a study reports the average age of tablet users is 34 years old and that the standard deviation of these ages is 15 years. We want to talk about the distribution of sample means, where we've taken samples of 100 tablet users at a time. And to do this, we're going to use all of the information about the original data set with the central limit theorem to talk about a distribution of sample means. The original variable, we'll call capital X, is the age of tablet users. So whoever ran the study that's posted on this blog talked to many tablet users and recorded their ages. The average age is 34 years old. We will use mu with a subscript x to denote that average. And the standard deviation, sigma, subscript capital X, is 15 years old. These numbers are going to help us talk about the distribution of sample means, but we have to first create a new variable. We're going to create the variable capital X bar, which is the average age of tablet users when we take samples of size 100. So we will collect, supposedly, we're not actually doing this, this is the theory behind it. We'll collect 100 tablet users, record the average age. That would become one value of our new X bar variable, and we would repeat this process until we had many averages from many different samples. That's the data set X bar. To talk about the distribution of X bar, we use the central limit theorem, which says the distribution of sample means will be normally distributed. So to get in detail about the normal distribution that represents capital X bar, we just need to know two parameters, that is the mean and the standard deviation. The central limit theorem tells us that these sample averages target the population mean, which essentially allows us to just copy over the mean from our original variable. So the original variable had an average value of 34. Our new variable has that same average. The standard deviation doesn't copy over, but it is related. The standard deviation for our new variable takes the standard deviation from the original variable and divides it by the square root of our sample size. So 15 divided by the square root of 100, since we're taking samples of 100, and that comes out to be 1.5. We now have everything we need to be able to describe the distribution of the sample means. It is a normal curve with a mean of 34 and a standard deviation of 1.5. Now we can talk about the probability that the sample mean age is more than 30 years. So to do this, I'm going to start by writing that sentence into mathematical notation. So the probability that capital X bar, the average age of tablet users, is greater than 30. I'll draw a picture to represent this distribution, labeling the average value, 34, and then at least 3 standard deviations above, as well as 3 standard deviations below, so that I get an appropriate scale of my horizontal axis. I'm looking for the probability that my X bar is above 30. So I find 30 on my drawing, put a vertical line at 30, and that's a sample mean. So that vertical bar represents one of the sample means out of the entire set of the average age of tablet users. Since I'm talking about a sample mean being larger than 30, I want to refer to the area to the right of X bar equals 30. To find that area, I'm going to first calculate some z-scores. So I want to know what the z value is for an X bar of 30. And we've used a formula before that looks like z equals x minus mu over sigma to take an x value and convert it into a z-score. But this is a little bit different. I'm not starting with a data value and finding a z-score. I'm starting with a sample mean. Now that sample mean, X bar equals 30, is one singular value from my new variable X bar, But just to clearly annotate this formula that we're going to use, instead of saying z equals x minus mu over sigma, I'm going to write it as z equals x bar minus mu sub x bar divided by sigma sub x bar. That way we really know that we're talking about all values that came from our new variable, the distribution of sample means. So I'm taking a value from my set of sample means, I'm using the average of my sample means, and I'm using the standard deviation of my sample means in this formula. I plug in my values and find a z-score of negative 2.67. And let's find the area using our table. So we're going to use the complement. If I want right-sided area, I have to find the left-sided area on my table first. So I'm going to convert the probability that z is greater than negative 2.67 into the complement, 1 minus the probability that z is less than negative 2.67. That area, z being less than negative 2.67, is 0.0038. So we do the difference there, 1 minus that area, and we find 0.9962. So very close to 100%, but just shy of 100%. There is a very strong chance that the average age of any one of these samples of 100 tablet users is greater than 30. Now let's find the 95th percentile for the sample mean age. Again, we're looking at our new variable, the set of average age of tablet users, since the question's asking us about the sample mean age. A 95th percentile is a value in our data set, or a sample mean in this case, that carves out the lower 95% of data. So we're looking for some sample mean that separates the bottom 95% of data from the top 5% of data. To do this, we're going to use our table where we look for areas that are close to 0.95. I can find two areas that are very close. One of them is 0.9495, the other is 0.9505. And 0.95 happens to be dead center between these two values. So we can take the z-scores from each of the two areas that we see on the screen and average them if we like. Averaging the z-scores 1.64 and 1.65, the two z-scores that correspond to the areas closest to 0.95, we find a z-score of 1.645. Now, they want us to find the 95th percentile for the sample mean age. And we have a z-score, but we need to convert it into a sample mean age. So we've done this before, where we've taken a z-score and converted it to a variable value. But this is slightly different because I'm not looking at the original variable set of x's. So I'm going to annotate this so that I'm looking at x bars, and I'm using mu and sigma from my sample means distribution. So the x bar that I'm looking for is 34 plus 1.645 times 1.5, and that comes out to be 36.5. So 36.5 years is the 95th percentile. And that basically means that someone who is 36.5 years old in this study is older than 95% of the other members in the same study.